welcome everybody to the September novice meeting tonight. For those of you who don't know me, my name is Chris Morisette. I'm the novice chair for the Houston Astronomical Society. And what we're going to be talking about tonight is observing Jupiter and Saturn. These two planets will be in opposition. So Saturn will be in opposition Saturday, and then Jupiter sometime in December. So we're going to talk about these two planets, and specifically, we're going to talk. Oh, and before I forget, if you have any questions during the course of the presentation, go ahead and enter them in the chat. And then when I finish up, I'll go back to the chat and we'll go through the questions. So what we'll be talking about tonight is the following. We'll talk about just some general concepts regarding viewing. We'll talk about, where to find Saturn, where to find Jupiter, why is this a good time for us to be viewing these planets, what kind of equipment would be helpful in our endeavors to view these planets. We'll talk a fair amount about that. And then we'll kind of get into some of the details around the two planets, Jupiter and Saturn, key facts, talk about their moons, talk about the dynamic nature of each planet, and hopefully just to kind of give you some background and make your viewing experience this fall more fruitful. So let's talk about viewing. And as I mentioned earlier, why now? Well, Saturn is going to be in opposition day after tomorrow, Saturday night. And with any luck, Saturday night should be a really nice night for viewing. So that's great fortune on our part. Jupiter, I'm covering Jupiter as well. And Jupiter will be happening later on in the fall. It comes into opposition on December 7th. So we've got a little bit of time before Jupiter will be in full bloom, so to speak, for us to view. But Saturn certainly is right there for the taking. Here is a copy of the skymaps.com monthly sky map. This one is for September, or the month we're currently in. And what I did is I went ahead and put a black circle with kind of a faint yellow fill to show where Saturn is in the night sky. So if we have this map and we're out on the driveway and we're facing south, we can expect to see Saturn coming up in the southeast, relatively close to the horizon in the early part of the evening, which would be 8, 9 o'clock for us this time of year. Shown a different way or from a different viewpoint, this is where Saturn will appear again in the southeast, rising up on the ecliptic through the course of the evening. And then with Saturn on Saturday night, we'll hit the highest point of its travel along the ecliptic around midnight. And you'll see that Saturn currently is passing through the constellation of Aquarius. So this will give you, again, another sense of where to look for Saturn out in the night sky. So why is opposition so important? Well, let's talk a little bit about opposition. Opposition is actually the closest approach that a superior planet such as Mars, Jupiter, Saturn, Uranus, and Neptune have to Earth. So when we're in opposition, as you can see from this diagram, the planet in question is at its closest point to Earth, which is nice because we're going to get the largest apparent view of that planet possible during our annual orbit around the sun. It will be low in the sky at dusk, as I showed on the previous two slides, but at midnight it's going to get to its highest point, and when it does that, we are getting better viewing because we're looking through less atmosphere. So this is again another picture to kind of illustrate the point of opposition and superior planets. Kind of shows you where, again, planets like Saturn and Jupiter appear during the course of the year, during the course of our orbit around the sun and their orbit around the sun. And this just kind of gives you, again, another view of that. When we're in conjunction, we're actually on opposite sides of the sun, and as a result, aren't able to view the planets during a period of time. And the other 2 points that you see here, we can view the planet, but it won't be as ideal as it is when the planet's in opposition. This is another slide showing showing Saturn is near opposition, meaning it's opposite Earth from the sun. Again, it's just kind of another version of the last couple of slides that we've looked at, but it kind of gives you here some distances, kind of shows you the difference in distances. You really do shave off a lot of distance between Earth and Saturn in this example when you're in opposition. I want to spend just a minute or two talking about retrograde motion. Now, in this particular animation, we're actually looking at the orbit of Mars, but it has the same principle applies for Jupiter and Saturn. So if you'll notice, I like to think of Earth and Jupiter and Saturn is kind of on a celestial track meet, or in a celestial track meet. Earth has the inside lane, while Jupiter and Saturn occupy these outside lanes. And as we pass those two planets, the apparent motion of Jupiter and of Saturn, and in this case Mars, appears to go backwards. And that's because we're passing that planet in this great celestial track meet that we're involved in. Now, if you remember back, and I want to say it was May, I gave a presentation on the history of astronomy, and in that we talked about Ptolemy. And Ptolemy was an ancient astronomer that used a mechanism or a tool called epicycles to describe and use, or to describe this apparent motion. And he had to introduce this artifice because he was dealing with or living in a geocentric world. That is, everything is revolving around the Earth. And so that was the mechanism he used to describe this. Once you began to realize, as they did in the Renaissance, that we were really in a heliocentric world and the planets were orbiting the sun rather than everything else orbiting around Earth, then you didn't need an epicycle or some kind of artificial mechanism to describe this. You could describe it in the way that this animation is showing you right now. So that's retrograde motion. And one other thing I want to point out is as the planet makes this circle, this apparent backwards motion, it hits opposition right about here, which is where we're closest to that planet during the course of both of our orbits around the sun. So a little bit about retrograde motion. This is a diagram that just shows you the retrograde motion timing for 2023, 24, and 25. It's not really easy to read. I blew it up a little bit, and unfortunately, things are a little bit fuzzy. But for Jupiter, this describes the timing for when retrograde motion in 2024 occurs. So you can see April, we're coming along here, or I'm sorry, February, March, April, and then when we hit June and July, we're actually turning back on ourselves. Here you see the circle right here. Now December is when we hit opposition, and it's not really clear from this diagram exactly where it's not really clear from this diagram that is in fact the point of opposition, but it comes through much clearer with Saturn. So here is the same picture, only with Saturn as the planet in question. And if we blow up 2024, we can see this retrograde motion in here in September. you can see it kind of lines up right in the center of that backwards motion loop that we looked at in the 2 or 3 slides ago. And so that kind of gives you, that kind of shows you where opposition occurs in relation to its retrograde motion. Another facet about opposition is, again, the key facet actually is, or a key facet is that we are viewing the planet at its closest distance to Earth. So in this particular picture here, you see a comparison between Jupiter at a point where it's not in opposition, where it's actually farther away from Earth than you see on the right, which is at opposition to Earth. And you can see just in looking at the apparent size here, there's a marked difference in the size of the planet. So that's really good because because we have that marked difference, the equipment that we have can give us a much better view, larger view, crisper view of the planet, depending on the telescope that we're using. So that is kind of the key thing about the having opposition working in our favor. So we'll talk a little bit about equipment for viewing. And here you can use just about any telescope out there. If you're going to use a refractor, you'll probably want to use something that is, I would say, at least 4 inches in diameter, if not more. Here you see a Takahashi that's a 6-inch telescope, which is really an ideal telescope for astrophotography. But you're going to need some light collecting ability, and 6-inch refractor is probably what you would need, although that's pretty darn bulky. There are better options here, I think, just for doing visual astronomy. Here's a Schmidt-Cassegrain telescope. I'm guessing that this one pictured is probably in the 6 or 8 inch category, or 8-inch, 6 to 8 inch diameter size. This is actually a really good choice for viewing Saturn. Because of the construction of this telescope, you can get more magnification than, say, what you would have with that Takahashi, and it's a lot more compact, a lot less weight to contend with. So Schmidt-Cassegrain is a good choice for going out and looking at Saturn and Jupiter. I think as far as bang for the buck goes, Dobsonian is probably your best bet. I have here, you can't see it here, but in my living room, I have a 10-inch Dobsonian with 2 or 3 different eyepieces that are relatively good quality. And this is an ideal telescope for going out and looking at the planets, Jupiter and Saturn, during this time of year. If you're going to get a Dobsonian, probably 6-inch you could get away with, but really 8 to 10 would be where I would start, and then anything bigger than that would just give you more magnification and viewing. One thing to consider too, though, when you get a larger telescope, your field of view is going to be more constrained. So you're going to have to pay special attention to whatever finder scopes you're using, such as a Telrad or just a small refractor that you put on that telescope. You may even need to change out eyepieces in order to find the planet and get it in your line of sight. But once you've got it there, then you can go to a shorter focal length eyepiece, which will give you more magnification. But just some things to consider as you're going out and viewing. This is a really nice diagram right here. This gives you a really good comparison of what Jupiter would look like in your field of view if you started out with a 3-inch telescope and worked your way up to an 8-inch or 18-inch rather. So on the bottom, what you see here is the apparent size of Jupiter through an 18-inch telescope. And then you can see the comparison on the top between the 18-inch and what you would see in this first column here would be what you would see with a 3-inch, a 4-inch, a 6-inch, 8-inch, 11-inch, 14-inch, and then all the way up to 18-inch. So the size, the diameter of the telescope really makes a difference in terms of the magnification that you get, and also the amount of light you can collect, and the clarity and the crispness of the object that you're looking at. For your particular setup, if you want to get an idea of what your field of view would look like, you can go to astronomytools.com, and once you go there, you can tell that the algorithms in there, hey, I want to look at Jupiter, and then you can put in what your telescope dimensions are, what your eyepiece dimensions are, and then astronomytools.com will give you kind of a field of view for what Jupiter or Saturn would look like in your telescope. So just kind of give you kind of a desktop study of, what to expect before you get out into the field. Magnification, it's going to depend on a couple of facets with respect to going out and viewing. So it's going to depend on your telescope's aperture or diameter, and it's also going to depend on seeing conditions. So let's talk a little bit about telescope aperture. If you've got a small telescope, like, let's, for the sake of argument, use the 6-inch Dobsonian, you can get a nice, crisp, clear view of Saturn in this example, but it's going to be relatively small. Now you can increase that view of Saturn by going to a shorter focal length eyepiece, but what's going to happen is you're going to begin to get kind of a fuzzier view of the planet. And the reason for that is because if you think about it, a telescope is a light collecting device, and a 6-inch telescope's only kind of collect so much light. So if you magnify that by going to a shorter eyepiece, you're really kind of spreading that light over a larger area, and you're going to get a fainter image. And then if you continue to go along that trek, you're going to get something similar to what you see on the right-hand side. So if you want to get a large view that's crisp, you're going to need to increase the aperture of your telescope, and that will allow you to collect more light and get a clearer, crisper view. So that's one aspect of what you're going to be able to see. Let's talk a little bit about seeing, though, and that is that is kind of a measure of the quality of the view that we get, that is dependent on the atmosphere and how much turbulence there is in the atmosphere. So, and how much atmosphere we're looking through. So when a planet is high in the sky, that's really ideal because we're looking through less atmosphere, which will give us less distortion and interference. So if you're looking at an object while it's on the horizon, you're looking through about 40 times more atmosphere than you would if you were looking overhead. So that's why opposition is really great, because we can get the planets high up in the sky during the middle of the night, and that's ideal. So that's one thing to consider, is we're looking through less atmosphere. The other is the conditions of the atmosphere. So in Houston, we have pretty stable conditions when it's warm around here. And the air is still, we get warm air that'll overlay cooler air. The atmosphere is relatively stable, and there's very little exchange of air vertically. So these warm, hazy nights in Houston are great for planetary observing. And in September, for all intents and purposes, we're still kind of in the thick of summer. Although it's cooled off a little bit, it's still pretty warm and hazy and humid out. So, Saturday night, barring any major change in the weather, we should get some great conditions for viewing Saturn. Now with Jupiter, we might have a little bit different situation, because we're going to be seeing that in opposition in early December. And typically after Thanksgiving, you can expect to see cold fronts and a lot of turbulence in the air, just due to kind of the winter weather that we get. And so when we get to December, we'll just have to see what early December's like. But you may get into a situation where you're going to have to, wait a night or two after a cold front comes through in order to let the atmosphere kind of stabilize so that you get a stable view of Jupiter. So just a little bit about seeing here that is helpful. Filters can really help out in terms of looking at various features on Jupiter and Saturn. You want to, just kind of as a general comment, you want to make sure that whatever filters you get match the diameter of your eyepieces. So if you have, and typically they're 1¼ or 2-inch diameter. So you just want to make sure you check before you go out and buy or borrow a filter just to make sure everything fits. Excuse me just a second. I'm going to grab a quick drink here. All right. So just a little bit about filters. Now, this is a really nice reference table that Agena Astro put out, and it covers all the planets as well as the moon. Not all the planets, but the planets that we typically will go out and look for. And I've got a little box kind of drawn around Jupiter and Saturn. And again, what you can do is you can use this chart to kind of say, hey, if I want to look at the belts on Jupiter, or if I want to look at the Cassini division on Saturn, what kind of filter should I be using? And in here you can use this table to say, okay, well, in that case, I'd want to use a yellow-green filter. If I want to look at the giant red spot or the bands and the rings on Saturn, then I'd probably be looking or contemplating about using a dark blue filter. So again, we'll talk more about the features of each of these planets, but this table gives you a really nice reference to say, hey, what kind of filter would help me look at some of the various features that you see here. Moon transits are big. So here on Jupiter, you might want to go with a dark red filter. So anyway, really handy table here. Okay, so let's talk about, so that's a little bit about viewing. Let's kind of dive in now and talk about the planets themselves. And we'll start out with Jupiter, even though it's coming up later in the fall. Just a few facets about Jupiter. It is the largest planet in our solar system, about 320 times the mass of Earth. You need to take 12 Earths side by side to get to the width of Jupiter. Jupiter is about 480 million miles from the sun, and it has an orbital period of about 12 years. So just a few facts and features, and then you can see how Jupiter, obviously Jupiter's the big brother of all the planets here shown, and it's considerably bigger than the 4 interior planets and Pluto. Jupiter's rotation is very quick as well. And this picture kind of shows a really stark example of that. So the picture that you see here on the left was taken at about 4:30 in the morning, and the giant red spot's here. And the picture on the right was taken less than a half hour later, and you can see a marked change in the position of the red spot, as well as one of the Galilean moons coming up over the horizon to orbit around Jupiter. So in a very short period of time, over the course of an evening, you get a lot of motion and a lot of dynamic action with Jupiter that you can actually film and photograph, make videos of, and just generally observe, which is really kind of the funnest way to do it. So as you're out there, take a look and get an understanding or a study on where particular facets are of the planet, and then when you go back a half hour or so later, make a note of where, how those have changed. Jupiter is composed mostly of hydrogen and helium. It does kind of have a solid rocky and ice core. but most of the planet itself is composed of metallic hydrogen and then liquid and gaseous hydrogen and helium. Transits and shadows, these are, again, one of the dynamic features of Jupiter in particular that are really cool to observe. I've seen the planets as they've come up over the horizon, and I believe I've seen the moon. I've seen the moons come up over the horizon of Jupiter, and I've seen them transit the planet. I'm not sure if I've personally ever seen a shadow, though. But you can see in this diagram or this video that Sonny Manley put together, it's very apparent. You can see the moon itself and its shadow as it crosses the surface of the planet, which is really fascinating to look at. And the reason we can see that shadow is because we have the sunlight from the sun coming at one direction towards the surface of Jupiter, and in Earth, our view from Earth is at an angle to that, and as a result of that, we're able to actually see the shadow as it transits the surface of the planet. And then here is again a final picture from Andres Salaveria, one of our members, and he was able to capture a really nice view of one of the planets or the moons, excuse me. I think this one's, well, it is Io. I'm guessing, but we've got it in the title name on the slide. But that's Io coming across in its final position as it transits, and you can see the moon distinctly along with its shadow. So really cool thing. And I would say if you're going to go out, and I want you to go out, obviously we wouldn't be giving this presentation if I didn't feel strongly about it, but I want you to go out there when you go out there to try to witness one of these moon transits, and to also see if you can spot the shadow of the moon as it's going across the surface of the planet. And then here's a really cool picture, and excuse me just a second, got a little bit of a runny nose tonight. Here is a really unique picture where you can see three of the Galilean moons along with their shadows as they're passing over the surface of Jupiter. Talk a little bit about the different formations or different regions of Jupiter. Here you see three different types of structures, one being the belts, and the belts are really these dark bands that you see along the surface of the planet, and these dark bands are where material is actually falling back down towards the core of the planet. And so this would be analogous in the case of Earth to rain or snow, material from the atmosphere coming back down. A zone, which is a lighter band, this is going to be an area of rising material. So in the case of Earth, where we have water evaporating and going back up into the atmosphere, same kind of phenomena on Jupiter, only you're looking at obviously different materials, probably hydrogen, helium, ammonia, things of that nature. And then the regions are at the poles. So we have the North Pole and the South Pole, and they're almost like instead of a band like we have with the zones and belts, it's more like a cap. So just a little bit about the structure of the planet, the way the atmosphere looks. And you can see that these clouds are in flux. So here is another animation that's really cool. It shows you material on one of the zones moving left to right. And you can see down here in the lower part of the picture, the great red spot is actually circulating like you would see with a hurricane here on Earth. So again, another dynamic feature of Jupiter. Here is a different view of that, kind of gives you a better, a clearer view. So you see the material in the zones going left to right, and then in the belts you can see the material moving slowly or slower, moving right to left. And here again you can see the circular motion of the Great Red Spot down here in the near the middle of the picture. So that's really cool stuff. One of the other things too that is really interesting about Jupiter is that some of the features on the surface of the planet will disappear. So in this case, what you see here is one of the belts disappearing, and you can see quite clearly here in 2009 you had a very distinct belt right here, and then after less than a year later, that belt has not altogether disappeared, but has diminished greatly in appearance. So again, another dynamic feature of Jupiter. And then another feature that we associate with Jupiter are these ovals, such as the Great Red Spot. And I guess here we've got Red Junior shown up here. And these structures can also disappear from view or combine with other ovals. So what you see here in this case is over the course of 3 years, you can see 3 distinct ovals here in 1997, whereas, over the course of the next 3 years, you'll see a merger of 2 of these, D and E and B and C, to combine and form this new one called BE. And then eventually this one called FA is moving towards BE and eventually merges with that. So you've gone from 3 ovals to 1. And again, just kind of highlighting the dynamic nature of the planet. Here's a series of pictures that we were able to get from various space probes that went out to look at Jupiter. Here's some views from Voyager 1. This is really cool. Here is another shot from Juno. And again, kind of this bluish hue with some of the almost kind of like sandstone color, really cool looking. My favorite one is this from Juno called the Pearl Storm. It almost looks like it has a 3-dimensional texture to it. It probably does, but I mean, just looking at it, it reminds me of kind of an impressionist painting from Cezanne. He used to use a lot of heavy brush strokes and get a lot of texture to his paintings, and that's kind of what this reminds me of. But these are some really beautiful shots and images from space probes that have flown in and around Jupiter. Let's talk a little bit about the winds of Jupiter. Jupiter does have some really severe winds. Typical wind speed on Jupiter is between 200 and 400 miles per hour, so very fast. The red spot, which you see circulating down here kind of in the lower right part of the image, that has speeds that are up to and greater than 400 miles per hour. And then up at the poles, you'll see wind speeds that can reach 900 miles an hour. So very fast, very strong winds on Jupiter. Another great thing about Jupiter, kind of not necessarily directly related to viewing, but something cool to realize about Jupiter is that it is a very large planet with a very big gravitational pull, and that's been a good thing for places like Earth because it acts as a magnet or a vacuum cleaner to kind of pull objects away from Earth that may do us harm. And so that's one of the great things about Jupiter. It's kind of like our big brother. It's helped us out, and because of that, we probably have been put in a position to develop intelligent life on Earth because we haven't been wiped out by some catastrophic event. Jupiter's kind of had our back, so to speak. A really vivid example of how Jupiter can take an object and pull it away and destroy it for us is the comet Shoemaker-Levy. Here you see the comet near its end, and what you see is Jupiter's actually pulling this thing apart. And then eventually the comet gets to a point where it impacts the surface of Jupiter, and you can see some of the impact scars down here, and here, and here. And again, a very dramatic example of how Jupiter can deal with objects out in space that could be a threat to Earth. Little bit about Comet Shoemaker-Levy. It actually was captured in Jupiter's gravitational pull back in the 60s or 70s, and it didn't fragment until closer to like 1992, and then the collision happened in 1994. So it was over a long period of time that Jupiter dealt with this comet, but it did so in a very dramatic way. Excuse me, let me get another drink here. All right. Okay, so let's talk a little bit about the moons of Jupiter. Jupiter has anywhere between 60 and 70 moons. I can't remember the exact count, but there are a lot of moons. The four that we know about or are most familiar with are the four Galilean moons, which are Io, Europa, Ganymede, and Callisto. And this chart right here shows kind of a comparison between those four moons and Earth's moon. And you can see that Ganymede and Callisto are bigger than our own moon, and Europa and Io, I believe, are smaller than Earth's moon. But that's kind of a nice comparison shot between our own moon and Jupiter's moon. So let's talk a little bit about the orbiting phenomena that the three inner moons exhibit. So Io, Europa, and Ganymede have what they call a resonant orbit. Now, in most cases, a resonance of any kind is very destructive. And I don't know if you remember back in your school days watching the old film clips of the Tacoma Narrows Bridge in Washington State, where the bridge was subjected to a relatively low wind speed, but the wind speed hit the same resonant frequency of the bridge structure, and over a short period of time, it basically tore the thing apart. So that's an example of where resonance can be destructive. Here, it's actually a stable self-correcting system in this particular case. So that's nice because that way we have it's nice when the universe, and in particular when our solar system is stable, because things are allowed to go on as they have been, and these three moons orbiting in a stable manner, I think, is a good thing. Here's Io, the pizza. They call it the pizza planet, probably more like the pizza moon. And I guess that's just kind of a general comment looking at the different colorations and shapes on the surface. But Io it's the most volcanic body in the solar system, and that is as a result of the tidal heating from friction generated within Io's interior as it's being pulled between Jupiter and the other Galilean moons. So there's a lot of force, a lot of strain, a lot of pushing and pulling that's occurring, and that energy is really heating up this surface and causing this volcanic activity. Some of these volcanoes will produce plumes that go as high as 300 miles, and the material in those plumes is sulfur and sulfur dioxide. So interesting facet about Io and the drivers behind its volcanic activity. Europa is primarily made of silicate rock and has a water ice crust and probably an iron nickel core. It's got a smooth surface, the smoothest surface of any object out there in the solar system, and this apparent youth and smoothness of surface has led to the hypothesis that a water ocean exists beneath the surface and could conceivably harbor extraterrestrial life. So that's Europa, very beautiful moon. Here we have Ganymede. It's composed of approximately equal amounts of silicate rock and water, and it has it is a fully differentiated or separate body with a iron-rich liquid core and an internal ocean that may contain more water than all of Earth's oceans. So that's Ganymede. And I'm reading from my script, so forgive me, but there's so much information here. I just want to make sure I get it right. And then here's Callisto. And Callisto is composed of approximately equal amounts of rock and ice. It has the lowest density and surface gravity of Jupiter's major moons. And this, the surface of Callisto is the oldest and most heavily cratered in the solar system. Its surface is completely covered with impact craters. Now, I gave this talk a couple of years ago, and I know Bill Spizzeri and I got into a discussion about that. Thinking was, hey, maybe our own moon really has that distinction of being the most heavily cratered. And I think where we landed on that was, you know, Callisto is a bit larger than our own moon, and it is older than our own moon. And you figure if both objects have been subjected to impact cratering during, you know, high bombardment periods, and maybe Callisto would have the edge here.
Well, Chris, so this is Bill Spizzeri. I just want
Yeah,
to tell you that since our discussion, I decided that I don't have enough time to count all those craters, so I really don't know the answer to that.
I got it. Yeah, me neither. So anyway, I think we'll leave it at that though, but I just did want to bring that up because that was a good question. Went back and did a little bit of research on that, and you know, hopefully we're able to satisfy your query about that, Bill. All right, so that's Callisto. So now we'll move on to Saturn. Saturn's one of my favorite planets. It's the rings are a real knockout. Saturn is the second largest planet after Jupiter. You can see here in this picture how it stacks up against Jupiter and then the other planets, much larger than even Neptune and Uranus. Here's another picture that kind of shows Saturn in context, at least in terms of its distance out from the sun. And a few facts about Saturn. Its orbit takes about 29 years to make one orbit around the sun. Its day is roughly the same as Jupiter's. It's about a 10-hour day. It's about 9.5 times as far away from the sun as Earth. So Saturn is about 890 million miles away from the sun. It has an axial tilt like the Earth, ours being 23 degrees, Saturn's being 27. Atmosphere is mostly hydrogen and helium, similar to Jupiter, and its yellow color is due to ammonia crystals in the upper atmosphere. And the weird thing about Saturn, and I'm still trying to get my head around this, but the gravity on that planet is about the same as Earth. And I would just have to, I guess it just has to do with the composition of the gases and the core in comparison to Earth. But I would have expected it to be much greater, but that's me. It's something I got to work out. This diagram here kind of shows you some different features on Saturn. You see the tiny core of rock and metal, similar to what we've got on Jupiter. And then you've got the ring system. composed of ice and water ice chunks, and that the rings are fairly thin. And I'm trying to see here. I think the average thickness of the rings is somewhere in the neighborhood of 1,000 meters or kilometer, but they're not very thick items. They're features. This shows you a picture of the rings of Saturn over the course of a 28-year cycle. And you can see from this picture that the rings will actually show themselves more and more to us at different phases in this cycle. But we will get to a point where we're looking at the rings edge on and we won't be able to really see the rings. And so if you look at this next picture, I have in this green box down here at the bottom, we show Saturn as it's going to appear to us this year. We'll still be able to see the rings, but they won't be as dramatic as they've been in recent history. And then next year, we're almost looking at this edge on. So next year, we may not be able to really make out the rings very well. Saturn would fit between the Earth and the Moon. So this gives you an idea of how large Saturn is. So, we've got a distance from Earth to the Moon of 239,000 miles, and Saturn and its rings would fit right in the center, right between the two. And then, like Jupiter, Saturn has belts and zones. So you see here the belts being the dark bands and the zones being the lighter bands. And I'm assuming, although I don't have this handy, but I'm assuming that they have the same feature of material rising in the belts or falling in the belts and rising in the zones. But I don't know that for a fact. And then you see here also, instead of a region at the poles, they have what they call hoods. And I'm not quite sure why they changed that, but that nomenclature. But that's what we have on Saturn. So again, a similar kind of topography for Saturn. And then, of course, you've got the rings, which are kind of their own beast. And we'll talk a little bit more about the rings here in a second. We know a lot more about Saturn from Cassini, which made its observations in the 2004 time frame. And one of the things, we talked about this a little bit earlier, and this is a little bit more information on the rings. And again, the average of 1,000 meters thickness of the rings is what I talked about earlier. But that's what the rings look like from up close. Here we see some of the gaps in the rings. So you have the Cassini division, which is really kind of the famous feature of the ring, and that's between the A and the B ring. So that's what you see right here, and that's about 3,000 miles in distance right here. And then you have the Encke gap, which is within the A ring, and I think that's what they're talking about right here. And it's a much narrower gap, in this case, 325 kilometers across. So that's a little bit more about the structure of the rings. Here is a really dramatic picture that shows, and again, this would be from a probe like Cassini, that's showing us the shadow cast by the main planet of Saturn onto the rings. Very dramatic here. The rings also have what they call what are referred to as spokes. So these are seasonal appearances, and you see here spokes that are drawn by an observer here on the surface of the rings, and then from Voyager 2, we actually see imagery that shows those rings. And the rings are thought to be caused by magnetic instabilities or uh, meteor, meteoroid, meteoroid, meteoroid impacts, he said 3 times fast. So those, in addition to having that nice circular um, configuration, can also have spokes at various times during its life. Like Saturn or like Jupiter, Saturn can have storms, and here's an example of a storm on the surface of Saturn. And then a weird thing here is that the North Pole has what is referred to as a hexagon, and this is thought to be a standing wave due to varying wind speeds. So, like if you've ever looked at the exhaust on a jet, maybe not when you're flying, but rather on TV when you're looking at some old NASA footage, you can see where there's actually parts of the exhaust that look to have a bulge at various points. And I think they call those standing waves. And this is kind of the same phenomena here. So very interesting. We'll talk a little bit about the moons. I won't go into all the moons of Saturn because Saturn has quite a few. We're going to pick out 4 for deep discussion, or more deep discussion than we'll have on the others. I'll talk about Mimas, Enceladus, Titan, and Iaptis. And before we get into those, Saturn does have quite a few moons, 83 moons, 53 named, and then there's countless small moonlets around Saturn. But we'll just go into the big hitters here. So here's Titan. This is the largest, the second largest moon in the solar system after Ganymede, and its atmosphere is 95% nitrogen, which I thought was kind of interesting. I hadn't seen nitrogen as a large component in really any of these planets or moons, so I thought that was kind of interesting. Mimas is really kind of an odd duck. If you look, it has a big old dimple on the side, on the surface of the of its of the moon, and this is thought to have been from an extremely energetic impact of some sort. And the hypothesis is that impact was so great that it could have split it in two or three or more. But very, very weird looking impact on Mimas. And not to be outdone, Iaptis has a very weird looking surface configuration as well. Most of the surface of this moon is bright ice, but on one side, it looks like somebody threw a chunk of coal at it, and it splattered and sprayed all over the surface of this moon. And anyway, one of the oddest, weirdest looking surface colorations that you'll see in any body out there in our solar system. Here is Enceladus. It has water, ice, water vapor geysers, and a vast under ice ocean. It's believed it has organic compounds and is one of the hopes for microbial life. And you can see, and I believe this is from Cassini, but you can see here the geysers that are emanating from the interior of this moon and erupting out into space. And really remarkable picture here. And again, I would surmise that this activity is occurring due to tidal friction between this moon and Saturn and the other moons in the orbit. So like we had with Io back on Jupiter. So very cool picture here. This one's really neat. This one is a eclipse that again would have to have come from a spacecraft like Cassini, where you were able to get behind Saturn and then block out the sun and then get that sunlight through the rings. So very cool looking picture here, and very inspiring. For more information, there are several sources out there. I'll just point out a few. Here is the Association of Lunar and Planetary Observers, or ALPO, not to be confused with the dog food. That would be a good source to get more information. Of course, Sky and Telescope magazine will be, I'm sure, running some articles and features on Jupiter and Saturn this time of year. Wikipedia is always good, Astronomy Magazine, and space.com. So these are just a few of the many resources that you can use to get more information on Jupiter and Saturn as we get into opposition. And with that, I want to just encourage everybody to get out there and look at these two planets. I will share with you the first time right after I joined HAS, I had a 6-inch Dobsonian, and I was out on the driveway, and I was looking at Jupiter, and I had to catch my breath when I saw the 4 moons out on the side of Jupiter. It was just awe-inspiring, and the bands and the belts and everything else. It was just wonderful. So get out there and look, and have fun. And like I said, Saturday looks like it's going to be prime viewing for Saturn. Okay, so with that, before I open it up for questions, I just want to mention that I hope everybody can join us for tomorrow night's discussion at the general meeting. This will be entitled Exoplanet Atmospheres with the James Webb Space Telescope, and this will be presented by Dr. Carolyn Morley, and I think she's with the University of Texas at Austin's Astronomy Department. So with that, let me do this. I'm going to stop my share, and I'm going to go to the chats, and I'm going to see if I can figure the chat out. So I've got a discussion between Bill and Joyce, and I think you two looks like you guys have answered but somebody's answered the question. So I'm not sure I don't think that's a question. I'm guessing that's not a question. So I don't see any questions in the chat. If anybody wants to just come off of mute and ask a question, please feel free. I'd be more than happy to do my best to answer it. And
so Chris, that was I'm sorry, that was about the Star Trek.
Oh, okay. So
yeah.
I got you. I didn't see any of the beers on tap listed there, so I was a little unclear. Okay, good. Yeah.
And just to remind everyone that the park verified with us today that we will be at Memorial Park on the 21st, and hopefully be able to see Saturn. And I don't know if you mentioned, but so there are rings that are different colors, and so on Saturn and so are those like different materials? Like why they didn't seem to be all the same color in the pictures.
Yeah, they may not be. I would guess that it's probably just the angle that the sun is hitting the material at. Like kind of like a prism effect. That would be my guess, but that's a good question. I need to go look at that a little bit closer. But I mean, it's all ice and white. Now there are some hard like materials in there, so that might also account for any difference in coloration. So it's not 100% water and crystals or ice. Yeah. That answer the question, Joyce?
Yeah, no, yeah, it's just yeah, I don't have a physics background, right? But I'm trying to kind of like understand or visualize like why we would have those bands and why it looks like different color, but yeah, maybe it's not. And then it's also interesting to me how how like the rings are actually quite thin relative to how
Yes.
large they are. And all I can really think of, it's like maybe like a pizza, like you're like kind of like spinning the dough, right? And
Mm-hmm.
you're kind of
Flattening it out.
so yeah. So yeah, it's interesting to think about.
Yes, I was kind of struck by that too, about how thin they were relative to their surface area. But yeah, they're not very thick at all.
Hey, Chris, this is Bill Spizzeri. I just wanted to say thank you. You covered all the bases tonight. That was a really complete discussion of the Jupiter-Saturn situation. Thank you very much.
Oh, well, thank you, Bill. I appreciate that. Very nice of you to say. I got one quick story for you. We're talking about going where no man has gone before. I just had the privilege of visiting Scandinavia last month, and I was in Stockholm, and I had two astronomy-related experiences in Stockholm. First, the Nobel Museum, Nobel Prize Museum is there. There were, they only give out prizes in physics, chemistry, literature, medicine or physiology, economics, and then there's one more that I'm sure I'm missing. Anyway, a peace, that was the other one, which Norway handles, which I thought was kind of weird. Anyway, a lot of the physics presentations were taken up by astrophysics, so there was a lot of information from Einstein and the general theory of relativity, Kip Thorne and his work on black holes and the cosmic microwave background phenomenon. So I guess what I'm trying to say here is I took a lot of pictures and gathered some information, and I'm hoping to put together a short supplemental presentation on that museum and some of the exhibits because I thought it was just fascinating, wonderful place. So that's the first story. The second story is the Doppler effect. As I was walking around the city and I heard the classic siren, the European siren, I heard the high pitch sound coming towards me and then the low pitch sound going away from me more than once or twice in there. And you always see that in the movies or on TV, and I just got the biggest kick out of that. And I was thinking about HAS when that would happen. So that was my experience with the Doppler effect in Stockholm. So I just wanted to share that with you. So anyway.
Hey, Chris, congratulations on making it all the way to Scandinavia. That's not a small thing to do. 5 years ago, I went to that same museum.
Yes.
And I came home with the Nobel Prize.
Sweet. Yeah, there you go. Hey, Bill, you're broken up. Are you on mute? Bill, we can't hear you. I can't hear you. Can you hear him? Anybody hear Bill?
Nope.
No.
Oh, now we can hear you. No, you're on mute now. There, try it now,
Okay.
Bill.
Can you hear me now?
Yes.
Okay. I went there 5 years ago to same museum. Absolutely fantastic. I came home with what looks like a Nobel Prize, but it's just chocolate covered in gold foil.
Oh, there you
They
go.
don't want anybody to have phony ones because, there's problems associated with saying you have a Nobel Prize when you don't. But doggone it, since you went through all the trouble of getting there, if I ever get to see you again, I can give you a Nobel Prize because of you completed your journey.
Okay, well, that would be fantastic. I'll accept on behalf of Kingwood. So.
And there's also chocolate inside it. So.
Oh well, that'll go great with Cabernet. So, what more could you want? All right. Well, listen. Any other questions for tonight? If not, thanks for coming. I appreciate it. I'll save our recording and get it posted. And with that, I wish you all a pleasant evening. So take care and get out there and look at Saturn Saturday night if you get a chance.
Good idea, Chris. Thank you.
You bet.